Okay, so we've been talking about the factors that control the flow of water through the ground, namely hydraulic conductivity and hydraulic head. And now it's time to put them together into the fundamental equation that is used to describe groundwater flow. So there was a French engineer in the 19th century named Henri Darcy, who was in charge of figuring out how to purify water for drinking in a French town. And so he began taking river water and diverting it through columns, big tubs filled with different materials, gravels and sands and clays and that sort of thing. And it was through these experiments that he sorted out a lot of the fundamental ideas that we now use to model groundwater. So in his honor, this is called Darcy's law. There's actually a variety of forms of this, but we'll start with the most fundamental equation, which is the equation for the velocity of groundwater. So this is Q is groundwater velocity, which is obviously in distance per time, often centimeters per second. So the velocity of groundwater is proportional to the hydraulic conductivity. That's a capital K for hydraulic conductivity. D stands for change in. H is hydraulic head. And X is horizontal distance. Okay? dH, dx together is basically the slope. You think of it as change in height, elevation over change in horizontal distance. It's like rise over run. It's the slope. It's the slope of what? Well, it's the slope of the hydraulic head, right? Where's the hydraulic head higher and where is it lower, and what's the angle between those 2 points? And it's basically the slope, and it's referred to as the hydraulic gradient. Hydraulic gradient, okay? So let's imagine that we have a land surface like this, and it's in a well-sorted gravel. And we want to know where's the water flowing and how fast is it flowing. So let's say, in reality, we would want to do a little bit more than this, but for now, we'll just make it easy. We'll think about this in 2 dimensions. Let's say that we drill 2 wells, and the sea level is down here. And we note that the water rises in the well up to this point, and it rises up to the well at this point. Oh, and a lot of people wonder about this negative. I'll show you what happens to this negative in a second. It's a directional component, and so it gets taken care of pretty easily. My computer's kind of funny here. Hold on 1 minute. Let's see if I can reposition that. Is that any better? Anyway, maybe it's a little bit better. Okay. So in order to calculate Darcy's law, we need the hydraulic conductivity. Well, the value for a well-sorted gravel, let's say, is 10 to the first centimeters per second. So that's easy. Now we need the dH and dx. So the first question we ask ourselves is, what is the hydraulic head in each of these 2 wells? Let's call this well A, and let's call this well B. And remember that hydraulic head is made up of 2 components. The first is the elevation from sea level up to the bottom of the well, where the water is going to rise in. That's the elevation head. And the height of the water from the time it enters the well up as high as it goes, that's the pressure head. So this is pressure A and elevation A. And I'll just give you some numbers here. Let's say that this is, 910 meters. And this is 60 meters. And over here we'd have the same thing. This is ZB, the elevation head for well B. And let's say that's 850 meters. And this is the pressure head for B. And let's say that's 130 meters. Okay. All right, so what direction is back up. What is the total hydraulic head here? Hydraulic head for A is the pressure head for A plus the elevation head for A, which is equal to 60 meters plus 910 meters, which is equal to 970 meters. And the total head at B is equal to the pressure head at B plus the elevation head at B, which is 130 meters plus 850 meters is 980 meters. Okay, so what direction is the water going to flow? Well, it's going to flow always, always, always from high hydraulic head to low hydraulic head. So in this case, it's flowing from B to A. So the flow is going to be in this direction, from B to A. So what we can do then is we can write Darcy's law as Q equals negative 10 to the first, which is just 10 centimeters per second, times the change in hydraulic head. We'll do B minus A, since it's flowing from B to A. So the H at B minus the H at A over the X at B minus the X at A. Okay. Since it's flowing from here to here, we'll call this 0, just in terms of its position on the x-axis. And let's say that we measure along the land surface to this point, and it's 1,000. Call that 1,000 meters. 0 meters to 1,000 meters. So can this be seen? Let me lift this up a little bit. So what we'd have then is Q equals negative 10 centimeters per second times the head at B, which is 980 meters, minus the head at A, which is 970 meters, over the X at B, which is 0 meters, minus the X at A, which is 1,000 meters. And we end up with, is it still visible, negative 10 centimeters per second times negative 10 over negative 1,000, which equals negative 10 centimeters per second times negative 0.01. That's supposed to say negative 0.01 right there, which is equal to 0.1 centimeters per second. Is that visible? Yeah. So the water is flowing from well B towards well A at that rate, 0.1 centimeters per second. And that's how we use Darcy's law.